Yeah, hi. Welcome back. Long time no see. Thank you for staying with me. It's really nice to see so many of you, also for my last and final lecture, even though you have to stomach me and my nasty handwriting for the second time today already. And before we start properly, I really want to thank you for engaging with me and all the great comments I got and questions I got during the talk and also after the talk. Thank you also for helping me with factors of 2. I really need it, so please continue to do that. And for practical purposes, I think we have an informal exercise discussion session today in the afternoon. I will be around here just in case if you want to discuss some topics in person with me. And then I owe 2 of you a bottle of wine. The 2 of you know who you are. I propose we meet after the exercise lecture at 18:30 in front of the restaurant, and you decide the wine bottle. And everybody else is welcome as well, but I'm legally bound to invite these 2 people to a bottle of wine. Okay? Now, with this out of the way, we are now ready for the grand finale of this excursion into quantum complexity and some fundamental statements about possibilities and impossibilities in the quantum realm. Okay, and in order to motivate today's lecture, we will really build up on the lecture of today in the morning. We will use these results and we would turn this insights into, let's say, maybe another interesting question. And so the goal for me, and what I want to share actually, and what I want to prove today, is not that most quantum circuits or quantum states are exponentially difficult to produce, but I'm interested in the growth of this complexity as quantum circuits become larger. Okay? So the motivation here is manifold. Some of the motivations actually come from physics, but it's also a question in computer science. If I work in the circuit model of computation and I start adding gates at random, then this is a random collection, right? And we would expect, also based on the second talk in the morning, that this is not very compressible in Kolmogorov sense, right? So intuitively we would expect that as we make these random circuits larger and larger, the complexity should also grow. Okay? And I think this lends itself to a well-posed question. Given a local random circuit, quantum circuit of size t, can we prove something about the complexity of this circuit, the incompressibility as a function of t? Okay, so what about complexity growth? And in order to gain some intuition, the result from today in the morning is very helpful. Because if we now envision a picture like this, where we start from the right and we start creating random quantum circuits of increasing size. What happens to the complexity in the sense that I defined it earlier today, the minimum number of gates I need to reproduce this functionality? Okay, and there's now 2 points that we understand. The first one is, what if my circuit has depth 0? What should the complexity be? 0, right? So this plot should start here. And then I hope it also makes sense for you that once this quantum circuit, this random circuit becomes exceedingly long, it will approach a generic random unitary circuit. And today in the class we proved that in this final regime, the complexity has to be exponentially large. Right? This is what we did today in the morning. So here, let's say after some circuit size order 2 to the power of n, the complexity is also of order 2 to the power of n, right? And now there's 2 possible questions. How do you get from here to here, and what happens afterwards? Let me first ask the question, what happens afterwards? What happens if we make our random circuits longer? Yes? Yes?
Then we will
Excellent. Yes, because a random unitary is invariant under random rotations. Random transformations, so additional circuits are like other unitary transformations. They don't change the measure, and so they don't change the complexity. right? Excellent. So I'm drawing these wiggly lines here, but we expect it to plateau. And there might actually be, kind of like if we wait long enough, there might be recurrence times because we have reversible circuits. So it's possible that it goes down again, but this is very unlikely. But if we do it long enough, it waits, but it plateaus. What would you expect here? How do you expect it grows? Like, roughly, what does your intuition say about random circuits? Like this?
You always have a circuit.
Yes.
So that, I don't know if that means it has to be low or if it has to be high. I think it
Yes.
means it has to be lower than like.
Yes, yes, very good. Kind of like the fact that we kind of like construct diagonal circuits, excellent observation, is a concrete realization of this circuit. So this is an upper bound on the complexity. So we know that it has to be below kind of like the diagonal of a linear growth with growth constant 1, right? The question is how much further below? Is it like this? Is it like this? Or is it kind of like a nice straight line? And today, we will kind of like prove that it is indeed a line. So that the complexity, it cannot grow faster than linear, for your reason, but we will actually prove that it cannot be slower than linear either. And we will not prove that by ourselves. We'll use a very powerful and interesting new result in quantum complexity from last fall, which arrived at the Simons Institute. Earlier results by myself and co-authors showed something like this, where kind of like the growth is of order omega t to the power of 1 over 5. It's kind of like polynomial growth. This is what we managed back in the day, or even 1 over 11. But there's a new powerful independent result that you can now use to push it to linear. Okay? And so this is the ambition of the last lecture. And I wanted to get there, and I've carefully planted the seeds that allows us to show this in the last lecture already. Okay? Are there questions or comments in this regard? Yes, this is like the definition of complexity is incompressibility.
Right, but this is of like the circuit itself and not of a single string, right?
What is a single string? Ah, sorry, yes. Thank you. This is true, even for the circuits. What we will do is this. States again, okay? We will do it for states. And this is already kind of like a strong indication that it is also true for circuits, but it doesn't quite solve it. But with additional machinery and the same ideas, you can also show it for unitary circuits. It's just a bit more heavy lifting. Thank you very much. More questions or comments? Maybe very quickly from my side, I think these questions are interesting fundamentally. It has something to do with circuit complexity. I care for this very deeply, and I guess I have an ally. In the other speaker of today also talked about circuit complexity a lot. I think this is interesting. It is also very interesting for basic physics questions. And I don't want to go into details here, but this is actually what motivated me working on this. Because random quantum circuits are today being used to model black hole phenomena, for example. Don't ask me why, but people do that. And they are kind of like to explain some physical properties, in particular Hawking radiation. It's very important to know, or kind of like people have assumed for a long time, that the complexity of a random computation inside a black hole grows. And this means that information is scrambled. And this is the proof ingredient of explanations of Hawking radiations and the black hole paradox. And more recently, at least in the US, this kind of like intersection between quantum computing and high energy physics and cosmology became a lot more popular, and even string theory. And the core principle is what's called the holographic duality principle. I don't fully understand it, don't quote me on that, but it is possible to relate a geometry of space-time in anti-de Sitter space to a conformal field theory on the boundary, which is essentially a quantum theory. And so kind of like people have noticed certain correspondences between objects you can compute in space-time physics and objects you can compute in quantum, and they managed to link them to each other in this duality. So you should really see this as a dictionary of a concept in space-time and a concept in quantum, and a link in between. And for a long time, a missing link and a challenge in this field was to find the analog of the event horizon behind a black hole in space-time. Kind of like a black hole kind of like sucks in stuff, and so kind of like the volume of its event horizon, if you let time evolve, grows linearly in time. Because linearly things kind of like as time evolves, more and more things is sucked in, and so there's more and more, a larger region of space-time that is hidden behind the black hole. And Lenny Susskind, one of the most prominent string theoreticians, suggested that complexity is the quantum counterpart. And so it was a big open challenge to prove that the complexity of a random quantum state also grows linearly in time, because this is the effect you would expect from the counterpart of the event horizon of a black hole in space-time. And he's a physicist, so he just kind of like did parameter counting and said it is natural to expect that this happens, but this actually proves it. And please don't quote me on any of this. I'm not a high energy physicist. I just wanted to point out there's interesting implications of this study outside of computer science. And it was also these questions that motivated me and friends to work on that and to come up with kind of like this first curve with the polynomial growth that recently by other smarter people was extended to linear. Okay, so how do we prove this? And before we prove this, I want to confess something to you. I carefully laid the seeds for such a proof already into the morning lecture. If you remember, I guess kind of like the arguments from the morning lecture were on a high level, we want to do some sort of counting. We want to kind of like count, kind of like that a generic quantum state, a generic vector on the sphere is far away from many other points. And we didn't do that by actual counting, but via concentration arguments. So the central result, the key lemma was if we choose a vector uniformly from a high-dimensional sphere, then with very high probability, it is not too close to any fixed vector. So kind of like when I have a vector, like if I have the North Pole here and I draw a point, then it kind of like with relatively high probability, it's not up here. It's kind of like pretty far away. And I presented you 3 different proof ideas, and you came up with at least one more during the lecture, and Amir had a really nice one, a geometric one after the lecture. But I chose this proof. I kind of like started with a uniform distribution on the sphere. Then I used the formalism to bound or compute all moments. And then I used this control of all moments to directly prove exponential concentration here via Markov's inequality and a Taylor expansion of the exponential. Okay? In more probabilistic terms, a uniform vector on the sphere gives me full control of all moments. I can compute and control them, whether I use Gaussian integration, geometry, or this high integration that I used. And if you have control of all moments, you control the distribution. And then you get exponential concentration. Okay? And this nicely handles the case where we're here, where we are already generic. Here we expect a really random distribution of our quantum state vectors that really follows almost the uniform distribution on the sphere, and so we have control of all moments. And they behave exactly like a random vector would. And here's the other extreme, right? We have 0 randomness, so it's completely deterministic. So we don't have control of any moment. Or not a single moment behaves like a random vector would behave. And maybe it intuitively makes sense in order to interpolate between here and here, we could use the moments. Kind of like assuming maybe if a circuit is kind of like a bit random sum size, then it's maybe reasonable to assume that it matches the first couple of moments of a uniform distribution, but maybe not the higher ones. And so as you become more and more random, your distribution should meet more and more moments of the uniform vector. Okay? And we will make this precise later. But kind of like, I really want to use the moments and this proof strategy to interpolate between a very structured circuit where we are not random at all, so most of the moments don't have this behavior, and a generic circuit where all of these moments have this behavior. Okay, so this is kind of like the goal is proof that states generated by size T circuits have complexity at least order T. This is what I want to do. And the idea use moments of VH squared to interpolate between structure, short depth, and generic behavior. Yes? Thank you. The same as in the morning. Thank you. A state vector has complexity at most r if I can find a quantum circuit of size at most r that takes a simple fixed initial state vector like the zero configuration and maps it to a state vector that is delta close in this fidelity distance. So that kind of like is almost parallel. And this delta is the quality of the approximation. And so this circuit depends on kind of like the type of gate set that we use, but kind of like the precise choice of gate set doesn't really matter because of the Solovay-Kitaev theorem we had yesterday. Kind of like, thanks, that was a good question. It was important that I remind everybody about this. Okay, and with this definition, the way that I proved the high complexity of a generic state vector in the morning was to really make a statement like above that tells you the probability of being very close to any fixed state vector is exponentially small. And so I need exponentially many of these fixed state vectors to have a chance of being close by. And this means that I need large size circuits. Okay? And I can make a similar argument without exponential concentration where I only use maybe not all moments but the first k moments. Okay? So here's the main result of today. Okay. Plane B. Oh, this is not good. Yeah, I'm afraid what goes up must go down, right? Suppose that H, the random vector, is still a vector on the complex unit sphere, is sampled from a discrete distribution that obeys expectation of H V H to L is approximately equal, or like in the easiest case equal, to the uniform distribution L, and we know what that is. We computed it earlier today. It's d plus L minus 1 over L minus 1 for L equal 1 to k. So for the first k moments, the new distribution I have mimics the uniform distribution on the sphere on the level of moments, but we don't say anything about higher moments. Okay? But no guarantee okay? Can we get a concentration statement? Then the probability, if I sample H from this new distribution, that the probability that it's close to a fixed reference vector is smaller or equal, then I think what I will get is k d 1 minus delta squared to the kth power, and maybe one of you can look in the lecture notes if this is really what we get. Okay? What is the idea here? What you can see is this is not an exponential concentration anymore, because it's not e to the minus d, but it's like kind of like, think about this scaling as d to the minus k. Okay, so the larger k becomes, the smaller this is, but it grows in a polynomial fashion. Okay? Grows in a polynomial fashion already looks a bit like this. Okay? And why do I do this? Because if we really think about kind of like a complex unit sphere, like I wrote it up, then if I average over the entire surface of this sphere, what is the expected vector I get? The barycenter. It's the core, right? This is kind of like the expectation of every point over the sphere. This is the first moment. I can get the same expectation value with two distinct points. Right? So I can actually find a very structured and discrete approximation of the uniform measure of the sphere for linear functions with just 2 points. And I don't know, this is a TCS conference, but this is something you might have seen before in numerical integration. This is kind of like the curvature rules or the quadrature rules that you use to discretize a sphere and to integrate functions. Okay? And there's actually a one-to-one correspondence. Because if I now want to mimic this function up to second moments, I also have to be correct for quadratic functions in expectation. This is what the second moment does. And so we need more points. But there is points that would do it. At least for this sphere, you could use the vertices of an octahedron or the vertices of a tetrahedron. And then you could go to third moments. And then you could use the octahedron still does it. Actually, if you have a spherical integration and you want to integrate a function of degree 3, you can still use the octahedron. And so basically what this tells you is there's bound to be kind of like discrete coverings of the sphere by a discrete number of points that allow you to reproduce kind of like the numerical values of all degree k polynomials. And this also means that you can kind of like get the moments right. And so this, what I'm doing here, is basically a partial de-randomization. A bit like how we use k-wise independence in pseudo-randomness. We start a simple proof where we use uniform randomness because then everything goes. And we know what to look for. The first lecture today was the uniform random case. And now we kind of like look how much randomness do we actually need in a k-wise independent sense in order to make these arguments work. And it's not bit strings here. This is quantum computing, so we don't use the conventional k-wise independence, but we use quadrature or curvature rules on the sphere because they kind of like tell us the moment behavior behind our concentration arguments. And if you think about it, if you kind of like use classical random bit strings, then you also tend to count moments because they tell you how much k-wise independence do you need. And then you kind of like, as an afterthought, you redo your proof. You try to get by with as few moments as possible, and then you write R, and by the way, you can do that with a two-wise independent function, and so it's basically efficient. Right? This is like a very similar idea here. The only difference is that I want to keep this kind of like moment value k, this k-wise independence, I want to keep this variable because this is my method. This is going to be my method for interpolating between structure and randomness. Like if you just imagine kind of like if you want to cover points on a sphere so that you kind of like do accurate integration or expectation of more difficult functions, you can start very, very structured. But once the functions become more complicated, the moments become higher, you have to cover the sphere more and more evenly. Until at some point, you really need almost every point on the sphere to make it happen. And so this is one well-defined way to interpolate between structure and a generic element on a high-dimensional sphere. Okay? The proof is kind of like very similar to what we did before, and it's not optimal. But I write down the thing I'm interested in. I have this new distribution. And I want to bound this. And what I did last time is I took an exponential here and an exponential here because this didn't change anything. And then I used Markov's inequality, right? But then I had a Taylor expression of the exponential and I needed all moments. So I can't do that anymore because now, by assumption, I have the first k moments and nothing beyond. What do we do? Well, here's what I would do. It's not the best way. Nothing interesting happens yet. I take the highest moment I still have and I take the power. And I take the same power on the other side. So instead of taking the exponential, I take the kth power. And now I do an inequality. Amir's word, something interesting happens. I do Markov again. A very basic inequality. And I get expectation value Markov. And now you see why I did k, because this is the largest moment I still know, I still control. And I know what it is. Sorry, I know what it is. So this is smaller or equal than d plus k minus 1 over k minus 1, 1 over 1 minus delta squared to the kth power. Now this is a binomial coefficient. I can bound this by k factorial over d to the k with 1, 1 minus delta squared. And I can bound k factorial by k to the power of k. And so I really get k over d 1 minus delta squared to the kth power. And this is exactly what I promised here. Okay? So a polynomial control of the moments gives you a polynomial tail-bound concentration inequality. And the larger the polynomial, the factor k is, the larger your control of the moment is, the better this polynomial concentration becomes. Okay? Note, however, that in this expression there's a glass ceiling. I get into troubles when I start choosing this k to be larger than d. So as soon as my moments become larger as the ambient dimension, this bound becomes larger than 1 and becomes useless. So this is a feature that will not allow me quite to get kind of like to circuit depth that are linear in the big dimension, but we will only get to circuit sizes which are kind of like the square root of the big dimension. So kind of like this is the magical threshold. Because if you have the square root of d here, if k is equal to the square root of d, then this is the square root of d, this is d, I still have a square root, and I still have kind of like this polynomial suppression. And as always, remember that in quantum computing, this d is 2 to the n. So this is already exponential concentration in the size of the system. Okay? And I would say this is very similar to really what we do when we analyze k-wise independence into randomized proofs. We also count moments, and then we kind of like try to get by with few moments. Then maybe the results are a bit weaker, but I don't need quite as much randomness. Okay? Now here's a corollary. A n-qubit state vector sampled uniformly from such a quantum k-wise independent distribution. And with this I mean the moment condition is true. If we have this, then the probability of, if I sample a concrete element from this new distribution, more structured distribution, that the complexity of H is smaller or equal than a threshold R, where the definition of complexity is here. Thanks again for reminding me. Kind of like this means that the probability if I sample a random vector from this more structured distribution, what is the probability that the complexity is smaller or equal than a threshold value of R? Is smaller or equal 2n to the 2r times this bound. And now I already write 2 to the n, 1 minus delta squared to the power of k. And what this means is this remains tiny until, and now forgive me, I have to cheat myself. until R, the complexity parameter, scales approximately as k times n minus log k over log n for constant delta. Okay? So this is a similar result to what we had earlier today. And it tells us that if we sample from such a moment distribution, where we have k moment, control of k moments, then kind of like the probability of having complexity smaller or equal than R remains extremely tiny until the circuit size we allow ourselves basically grows linear in k. Okay? And there's like some nuances. There's a log factor here, and this is the burn-in period. Kind of like this tells you that if k becomes exponentially large in n, this might become negative and the bound becomes vacuous. But in a regime where this is not the case yet, we basically see a linear correspondence between the complexity of the quantum states and the number of moments we control. So you should really see that we have to increase the circuit size of an approximation linearly in the number of moments that we allow. A really linear correspondence. Looks pretty good, right? This is also linear. And again, the geometric picture here should be, I first compute something for the entire high-dimensional unit sphere, and I assume that I can randomly sample from this. But this is kind of like structureless. This is a very difficult process. And so I don't use the sphere, but I use structured point sets that kind of cover the sphere evenly. And then when I make these point sets denser and denser, they more and more accurately approximate the actual sphere, in the sense that the uniform distributions on these points resembles the moments of the uniform distributions to higher and higher degrees. And what we just showed is that in this case the complexity also has to grow. Okay? And again, this is kind of like the spherical story, the complex unit sphere story of k-wise independence. There, if you have n-wise independence, you have a uniformly random bit. But with 2-wise independence, you can have a very structured set of bit strings, but it behaves like the uniform random bit strings for, let's say, size at least pairwise functions. And this tells you that the complexity of this set cannot be 0. And as you increase the notion of k-wise independence, your dictionaries, the point sets must become larger and larger, and so also the complexity must grow, just by counting. Okay? This is the quantum version of this story. Is there questions or comments at this point? It's either a very good or a very bad sign. I mean, if I were you, there's a very obvious question I would ask now. Do these point sets exist? Or is this kind of like just an abstract concept? Kind of like these k-wise independent distributions. I just defined them as a means to an end, to de-randomize an exponential concentration argument. This is all well and good, but can we build these things? Do they exist? And the notion of a complex projective design. A discrete distribution Pi Hi as a subset of the complex unit sphere is called a complex projective K design if the expectation over the new point set, H Kronecker product K, this is the same as I go over all the points Pi, Hi, take the outer product, take the k-fold tensor product, is equal to d plus k minus 1, k minus 1 projector onto the totally symmetric subspace. This is the high integration formula I had on the white blackboard earlier. This is the multilinear algebra version of demanding that the left-hand side, which is the average over your new point site, is equal to this projector, which is the integral over the full unit sphere of H star Kronecker K, dH. Okay? So this is the multilinear algebra version of demanding that if I integrate any degree k polynomial with respect to the unit sphere, I have to get the same expression as if I were to average it over a discrete number of points. This is kind of like the precise definition of a quadrature on the unit sphere. I just wrote it down in multilinear algebra language. We could also write, if for any homogeneous polynomial of degree 2k, the numerical average over the points evaluations is the same as the integral over the entire sphere. Okay, this is just the tensor product version of it. And then you can also define an approximate design, epsilon approximate k design, if, and I guess you can guess what happens if this average star Kronecker K is not too far away, d plus k minus 1 over k minus 1 p v k in some matrix norm. We usually choose the nuclear norm. This is basically means that this is true approximately, and in the quantifiable sense, in the sense that the integrals or the averages are most off by at most epsilon for any possible polynomial. Okay, so this is kind of like the approximate version where we're allowed to wiggle a little bit to not require infinite precision. Okay? Yes. Thank you. And maybe kind of like to have everything normalized even. A multiplicative accuracy is enough. Okay? And here is kind of like the first fact that I need in order to not be completely embarrassed in front of you. Fact, these things exist for every d and every k. So such quadrature rules exist. I think this was kind of like an open problem, but I think roughly 10 or 12 years Bondarenko kind of like used Brouwer's fixed point theorem to prove that you can always construct these things. So this is good. I'm not talking about the empty set here. But it is a non-constructive proof. And something that might interest some of you, just as a side trajectory, these sets have to become larger and larger when I increase the moment control k, because I have to approximate more and more complicated functions. And so the number of points has to grow like this combinatorial factor. with not minus 1. And this is always larger or equal than d to the k over k factorial. It's kind of like the size of these point sets must grow quickly. Does anybody of you see why? Yes. In the ideal case, I have to reproduce the projector onto the totally symmetric subspace. And this is the trace of this projector, so it tells you how many dimensions it has. It tells you the rank of this projector. On the left-hand side, I add a discrete number of rank 1 matrices. The number of rank 1 matrices I must add must be at least as big as the rank of the matrix I want to produce. And so this tells me a nice kind of like lower bound on the size of these sets, and you can see that they become very, very quick, very, very quickly.
The distance of
Yes.
designs, is there any k for which this is easy to see, like for k is 1, for example?
Yes.
Is this easy?
Take a basis.
Okay.
Kind of like we had it here on the sphere. Kind of like just take north and south pole. Then any linear function.
Yeah. So then, like, at what, like, is it easy for any finite k, or like, sort of where's like, at
Okay.
what point does it become non-obvious that they exist?
Well, here's kind of like, at least for the normal sphere like here, you can really use Platonic geometry to kind of like go up to order 3 or 6, depending on how you count. But then you kind of like run into troubles because you can show that there's kind of like, in order to get these point sets for 6 already, you use the orbit of a maximal subgroup of the full orthogonal or unitary groups. So you can't have a group construction that gets beyond. And this seems to be a glass ceiling for any dimensions. Kind of like typically you can't get beyond k equals 3 with a group construction. Because kind of like the Clifford group that I mentioned yesterday is a maximal subgroup of the unitary group, and that generates you a k equals 3 design as an orbit. But because it's a maximal subgroup, the Solovay-Kitaev theorem tells you that you can't make it bigger. Okay? And then there's like some, as you might expect, there's like some special cases. Like I think in dimension 24, the symmetry group of the Leech lattice gives you an 8 design. But in general, kind of like nice group theoretic constructions don't work because kind of like the group structure is not there. Okay? But this is not good enough. You should feel cheated still. I claimed I will make a statement about random quantum circuits, and here I am talking about Leech lattices. Something big is missing, right? And this is true. And here is a remarkable result that was defining for the study of quantum complexity and also quantum algorithm designs for the last almost 10 years. It's a theorem by Fernando Brandão, Aram Harrow, and Michał Horodecki from 2016. So 9 years ago. They state that local random quantum circuits of size, and I don't recall kind of like the right kind of like correspondence. I will just write, I think it's order n t 11 k11, I think log 1 over epsilon, something like this. It scales linearly in n, I think, or maybe quadratically, like the 11th power in k, and logarithmically in the approximation generate epsilon approximate k designs. Okay, so the idea is I take a random circuit of size, let's say k to the 11. I apply it to a simple initial state vector, and this gives me a new state vector, a new unit vector, and the collection of these unit vectors formed an approximate design. So what they really showed, and this has long been suspected in the community, is that when you study random circuits, random quantum circuits, and to increase their size, they become less and less structured and more generic, which is very similar to this notion of the K-design I had before, and it was long suspected that the two things are in fact the same. And the first result in this direction is by these three people from 9 years ago. And it's not perfect because it has this 11th power here. So conversely, if I take a random circuit of size t, it is an approximate t to the 11th root design. Okay? And now you can see where this comes from. Because basically this result of us a couple of years ago is basically this result, and then using local random circuits to generate these sets. And with the result by Brandau, Harrow, and Horodecki, we lost. Because the kind of like the correspondence between design order and size has an 11th power. And so we had an 11th power here. Last year in the summer at Simon's. Yes?
Can you say again what you mean by local?
Great. Can I just write this and then I say it? And last year we had a breakthrough because there was a workshop on, I think, quantum complexity at the Simons Institute, and some of the smartest people in our field came together, and they went from k to the 11th to k. This was an open problem over the last almost 10 years. Many people tried it, and there was sequential progress. Like a couple of years ago, we knew it has to be t to the power of 5. But last summer, they brought it down to linear. And now we know that the two concepts are actually the same. And now, to come back to your very good question, Bruno, what is a random quantum circuit? And the idea is that I kind of like operate in layers, in R layers, if I have a random quantum circuit of size R. And at each layer, I have kind of like n qubits, and I have an elementary gate set. For example, Hadamard T and C naught. And then I choose 2 qubit locations at random and apply one of these gates uniformly at random. Okay? And then I go to the next step. This is kind of like the easiest model. There's alternative models where I think equilibration happens faster, like this brick wall circuit, where you kind of like take a generic 2 qubit unitary and brick wall them together. And there the same results are also true. But it kind of like means that every step you choose a random location and a random gate and you add it, and the size tells you how many layers you do. Okay?
Just to be clear, every layer has like at least n minus 2 identities.
Yes. We just take kind of like one non-identity gate. And so kind of like really size is kind of like, there's a lot of room for parallelization. It's kind of like really linear growth. And I don't want to go into the details of how to prove this. It's very non-trivial. Instead, I want to give you an analogy, which is kind of like these beautiful card shuffling results by Diaconis. Maybe you know them. It's like one of my favorite results. Diaconis, mathematician and wizard, kind of like studied how shuffles actually kind of like create uniformly random permutations in decks of cards. And so more generally speaking, what is a shuffle is kind of like you permute a couple of very few cards, and you do that in sequence a couple of times in order to approximate a permutation of the full set. Because if I want to generate the permutation of a deck of cards, I would shuffle it like a baby. But professionals use shuffles. And this is a very interesting question in group theory, kind of like you have a big permutation group, and now you apply a sequence of smaller perturbations, but you do this over and over again. When does this sequence of smaller perturbations converge to the uniform distribution of the larger group? And I think Diaconis amazingly showed that you have to do 7 shuffles, 7 complete shuffles of a deck of cards to show that there's basically no mutual information between the initial configuration and the final outcome left. And I think if you do 6 or fewer shuffles, the mutual information is almost maximal. So kind of like really prove the sharp phase transition here. And in a way, these results are similar. Because what do I aspire? I aspire kind of like a big unitary 2 to the n by 2 to the n matrix on n qubits. And how do I generate this? With a random circuit that acts like a random unitary on smaller systems. And this is like shuffling. And now I shuffle over and over again. And how often do I need to shuffle? Until this sequence of local unitary transformations on individual Kronecker factors approaches a global random unitary on the full scale. Okay, this is basically the question. And with this K-design notation and these new results, you can actually do this in a more fine-grained way and ask yourself, how often do I have to shuffle until I get the first 2 moments right? What about the first 4? What about the first n? And these results, they're not quite as sharp as Diaconis. They still have a big O notation, but they tell you that kind of like the number of shuffles or local unitaries you need scales linearly in the number of moments you want to control, up to a certain threshold where a random distribution of the big unitary is reached, and then you plateau like you said. Okay? And with this result, we now prove this. What does this mean? The probability of, if I take a state vector which arises by applying a random circuit of size t to a fixed initial state, the probability that the complexity associated with this state, C delta of h is smaller or equal than r, is tiny until r is approximately t. This is what incompressibility means. And if you want the exact formulas, you can see it here. And with the results from this summer at Siemens, we can replace the k, which was the design order, with the size of a random circuit. Sorry, this k. Okay? Complexity in random quantum circuits grows linearly. There's one last detail. Today in the morning, I was very happy to share with you that these probabilistic assertions allow you to translate into a quantitative statement. If the probability of randomly sampling a point and having a small complexity is tiny, and we have a uniform distribution over the entire sphere, we can use Laplace's definition of a probability to make a quantitative statement. Laplace says, with uniform sampling, the probability of an event is the number of good events over the total number of events. If the probability of small complexity is tiny, we know almost all elements in my set have to have high complexity. This is not so clear here anymore, right? Because these finite point distributions might be weighted. And if you actually generate them with random circuits, they might have biases, because they are not nice point sets anymore, but they are kind of like they arise from creating random circuits. And quantum circuits are reversible. So maybe some finite states occur more frequently than others. Okay? So it could be that these are kind of like highly spiky distributions, and that the probability is very, very small, but for the wrong reason, that you might kind of like there's maybe just one high complexity state vector, and you always get this with very high probability, and all the others are low complexity, but the probability of getting them is not so high. What I want to say is kind of like with these random circuit constructions, the weights or the probabilities are not necessarily uniform. So I can't turn these probabilistic statements as they are into quantitative statements. But you can use again the control of the moments to show that this unbalance cannot be too strong. In words, you cannot have a good approximate k-design if one state vector is kind of like happens with a high probability and all others almost don't happen. This doesn't work. And so kind of like this translation to a quantitative statement can still be done approximately. So this means that not only does a typical random circuit generate states with growing complexity, also most conceivable circuits by this counting argument have to generate high complexity. And the number of circuits that don't generate high complexity is very, very small compared to the total number of circuits I can build. Okay? With this, I'm done, and I want to thank you for your attention, for working with me, and for the opportunity to speak here. Thank you very much.